Dr. Mark Sherman is the Technical Director of the Cybersecurity Foundations Group at CERT within CMU's Software Engineering Institute. His team focuses on foundational research on the life cycle for building secure software and on data analytics in cybersecurity. Before coming to CERT, Dr. Sherman was at IBM and various startups working on mobile systems, integrated hardware, software appliances, transaction processing, languages and compilers, virtualization, network protocols, and databases. Dr. Sherman received his undergraduate degrees from MIT and his PhD in computer science from CMU. He has published over 50 papers and several books on various topics in computer science. Please help me welcome Dr. Mark Sherman.
Good morning, everyone. Hope to have some fun today. I'm going to do a slightly different thing than what most people do. I'm not going to go in depth in a particular area, but I'd like to just share with you some of the work that's going on generally. And you'll see that my slides have a couple of comments and then a bunch of references on them. So if something tickles your fancy, you can go ahead and dive deeper into it later at your own leisure. I just skipped over the required legalese, if you permit me to do that. So, many of you may not understand, at Carnegie Mellon University, there is a separate DoD-sponsored organization called the Software Engineering Institute. We're about 650 people or so. Approximately 2/3 of the institute does cybersecurity. And again, most of those people are the technical staff. We've been around for quite a while, and approximately $140, $150 million of research going on there every year. It varies with federal budgets and things of that sort. Now, the reason why the DoD is interested in having an institute that focuses specifically on software engineering and cybersecurity is that it's really key now to how the government and how the DoD works. We had an Air Force general come by and he said, "I used to win wars by bending metal better than the adversary. Now I write better software than the adversary." That is where the focus is in trying to build the new sets of weapon systems in defense of the country. The problem is that there are a lot of bugs, frankly, that result in vulnerabilities. Now, we've analyzed millions of lines of code for both commercial and government sponsors. And we have fairly good confidence that on average, and again, there are exceptions on both ends, you will find one exploitable vulnerability in every 10,000 lines of code. So the example here was a 10 million line of code weapon system will have between 300 to 1,400 exploitable vulnerabilities in it. Put that a little in perspective, the F-35 weapon system, the stealth fighter, that has about 35 million lines of code in it. If you talk about a high-end automobile today, that has about 100 million lines of code in it. So, as we build the kind of stuff, even the best practices wind up shipping things that get put into practice that have exploitable vulnerabilities in it. So, how do you address this? Well, we do a lot of things in CERT. We do insider threat. We have more to talk on that later, another presentation on that later. We do malware analysis. We do organizational resiliency. We do intrusion detection, all sorts of things. This particular group, the particular talk, is sort of at the beginning of the life cycle. How do you build things better? Why do we do that? Well, if we take a look, almost all the problems that get introduced early in the life cycle. That's where the mistakes are made. Unfortunately, because of the way that we prioritize our attention, they're usually found at the end of the life cycle. In fact, we like to spend a lot of money on emergency rooms and trauma surgeons, not so much on vaccines. And if you look, frankly, at the vendors that are here, you'll see almost everything that's on the tables there is about how to deal with an attack after it's happened, or how to detect an attack that has happened. It's not about how you build something to prevent that to begin with. And as a result, we spend enormous amounts of money trying to fix that. So what can be done? Well, this conference is specific. There's a whole lot of things that can be done. This conference is about artificial intelligence. So I'd like to share with you just some ways that artificial intelligence is starting to be used to improve how software can be built. Now, I expect that most of the people here are not hardcore software developers. I don't think there's a huge contingent from IBM or Microsoft or Oracle, or even from the financial institutions. Those are places where you see enormous amounts of software being built, or some DoD contractors. They build a lot of software. Most people here only build modest amounts of software. They have a team that will build a web application or a mobile application, or they'll buy 3 or 4 packages and they'll connect them together, which is still more software development. So some of these things you can apply in those kinds of situations as well, and sometimes they're things that you ought to be able to ask your vendors about as they provide more information. So let's talk about the life cycle. What happens at the beginning of the life cycle? You have to know what the bad guys are thinking of doing. So one piece of research was done by IARPA, a wonderful office that I think has a great title. I can never remember the exact title. I think it's, oh, you can't even read it. I think it's the Office of Unanticipated Surprise or something like that. But it's a real office, and they sponsored research to go out and look at what they called unusual sensors, behaviors that are out in the network that kind of tell you what the bad guys are thinking and how they intend to come after you. And from that, you can start generating requirements in order to build more secure software. Now, that sort of tells you some sort of, if you like, intelligence. The actual mechanics of building software has a lot of AI involved in it as well. What would be the ideal kind of situation? What would be the vision of using AI? When I use the word AI, I mean sort of in the classical sense, which was something that kind of performs like a human would perform at a particular kind of task. That, at least when I went as an undergraduate, that was kind of the definition they gave us. It was not about search or first-order logic or all sorts of things. It was, can you make a program that behaves like a computer does? So, can, in fact, you write something that will take the specification of a program, high-level, abstract, and automatically generate computer the code, do all the right things? That was the golden idea. It's an idea that's been around for a while. In fact, if you read the original report, back in the 50s, they had what was called automatic programming, the beginning of AI, and it was this magical idea. A scientist would write down in very abstract terms what they wanted to do, and it would automatically generate programs. Remember, here, in this time, humans were standing in front of switchboards, toggling switches in order to put binary codes into computers in order to make them work. This was considered a huge step forward, if you like, the beginning of AI and building programs. So, you want to use AI, go write a Fortran program. But practically, let's sort of move ahead 50 years or so. The ideal hasn't gone away, but there are now much more advanced techniques that are available. For example, the Spiral project. In the Spiral project, they take a high-level specification of a system, and it uses what you now think of perhaps as classical AI techniques. It does some hill climbing, it does some first-order predicate logic analysis, and from that, it not only generates the algorithms and the code, it goes even further and says, what should specialized hardware be built in order to improve the performance of the inner loops that are in that code in order to build a high-performance system? And again, this is all research that's available. If you like this particular kind of system, you can actually go read about it, download it, try to use it. Going on to sort of more conventional things that people have, finding vulnerabilities in source code. This has now become pretty routine in most programming shops. You buy your favorite industrial tool that does source code analysis, and it will spit out all sorts of things that it finds wrong with your code, including vulnerabilities. Now, from the AI, most of that work is done with compiler kind of technology, and there was a talk yesterday that went into somehow data flow and a variety kind of other things that are in compilers. It turns out that AI is now starting to be introduced in these kinds of things as well. And what it does is it actually treats a programming language like natural language, sort of like English instead of like context-free languages, if you're familiar with those kinds of things. And as a result, it's starting to find new kinds of issues, new ways to find problems in programs. There actually is another talk later today that delves into this a lot deeper, so I'll sort of stop at that point. A challenge with all of these systems, however, is they generate huge numbers of false negatives. When I say huge numbers, I'm talking about things like 10,000 diagnostics that get spit out over a typical kind of program that a programmer has to look at and analyze. If you talk to the vendors, they'll tell you to do one of two things. The usual thing they will tell you to do is turn down the sensitivity so you get only a few number of diagnostics that you have to deal with. That's great. It improves programmer acceptance, because with the 10,000 one, what happens is they just throw them all away and they never get looked at all. So instead, you get a small number, but you know that there's a lot of stuff that's going through that shouldn't be going through. A way to try to deal with that is, again, to use AI to improve it. So there's another set of research that's being conducted that uses multiple analyzers and then artificial intelligence to compare the results of those analyzers, consider the context in which everything is going on, and be able to automatically say, of these 10,000 ones, well, that's what tool 1 said, that's what tool 2 said. By the way, I see the context that this program is operating on is like this. Those are the ones that are really the diagnostics that you should believe, and the other ones you can ignore reasonably safely. Now, this has a lot of promise. Again, there are now aggregator tools out there that you can go either download or buy, depending whether you like open source or commercially supported tools. But there's an interesting story that came with this particular set of research that illustrates the notion of train like you fight, the sort of military way of doing things. This applies here in AI. There is a huge data set of labeled data of bad programs called Juliet, developed by the NSA, made available through NIST. If you look at these generated sets, it starts with a header, it lists the CWE that's a problem, it has some function calls, it has the problem that's in the code, and then a diagnostic saying, you reached this particular piece of the code, something like that. Thousands and thousands of those files. Ran it into the training system. Training system came, I have a great way to find all your problems. Anyone want to make a guess as to what the training system found? It said that if you have a tool, and the tool says there's a problem on line 42, you'll probably have a problem. Why? Not because it knows what's going on line 42, but it just read 10,000, quote, problems, and by design, line 42 is where the NSA always injected the problem in the code. So it just illustrates that when you buy any of these kinds of systems, you have to make sure the data set's being used at is the one that you want. Now, there's another set of research that's going on that has been historically part of AI and has been a sort of a resurgence. And it's part of what's called the HACM project that DARPA started, but this is available in commercial tools as well. Early in AI, there was this notion of representing knowledge as first-order predicate logic. That faltered because the theorem provers that were needed didn't operate very fast. And for the theoreticians, it's known that proving these kinds of first-order predicate logic theorems is NP-complete, really hard stuff in the worst case. So over the years, we've had the advantage of Moore's law and a lot more work on heuristics that make sure that you can actually, in practical circumstances, do the theorem proving. And here, this particular collection of companies, a lot of aerospace companies building avionics systems, are able to apply these kinds of predicate logic techniques in order to go and prove that their programs are secure. Well, that takes us into building. Let's move a little bit into testing. There's a particular testing technique which is very simple but remarkably effective. It's called fuzzing. Basically, you take your program and you throw garbage at it. You just throw random stuff at it, and surprisingly, many times programs crash. Well, that worked great in the beginning, but it also is typically very inefficient. If you want to try all your inputs that have an integer input, going from minus 32,000 to plus 32,000 can take a long time. So instead, they've developed AI techniques, a lot of different ones, by which it can use AI to generate what those inputs should be into this fuzzing kind of tester. One way is to look at a bunch of sample files, induce or deduce what kinds of structures those files have, and then generate programs that files that look like those structures but are off in one way or another. Another way is to just find some starting point, like you did with the random one, but then use hill climbing techniques. You start to perturb it some way or the other, trying to crash the program. And again, these have proven to be very effective at being able to test. Finally, there's a lot of work being used to combine all of this together. For those who have never heard of it, there was something called the DARPA Cyber Grand Challenge. The goal here was, sorry?
Thanks for the advertising.
Okay. the Cyber Grand Challenge, and where people had programs and they had the different performers actually attack each other. More importantly, automatically find, fix, and redeploy the programs. And it used a variety of AI techniques in order to do that as well. It used concolic execution. It used statistical analysis. It used a variety of different ways to organize what was going on and then to build new programs that were more resilient to the attacks. It was quite an affair out in Las Vegas, which is what that picture was. And again, all of this stuff, you can read about it in the open literature. Part of advantage of government contracts is the people involved have to publish what they do. Now, speaking about DoD, if you talk about most government programs, planes, transportation, energy, they usually can't get perfect properties, that nothing can be attacked or nothing can fail. Instead, they have this notion of assurance. And if I say software assurance, the vast majority of people will say, I know what software assurance is. This is Microsoft Enterprise Licensing Program. But in the government, what assurance means is that there is a mechanical, usually manual review of information and evidence that gives them confidence that this plane is not going to fall out of the sky, two recent exceptions perhaps, but that cars, when they crash, have the right kind of safety features and so on. That kind of assurance is called software assurance within the military, and sometimes within other parts of the government as well. And that requires you to look at a lot of different things: output of test tools, reports from architects that did code reviews, and so on. It turns out that these kinds of assurance reviews, they do it for drugs as well, take an enormous amount of time, a lot of individual experts who have to read through everything. AI is being used here as well. In this case, things like the Watson technology from IBM. This was the Q&A piece of Watson. Watson is a big brand now with IBM, but the time this was done, it meant the Q&A stuff that you saw on Jeopardy. To look at all of these documents and be able to extract the information that the auditor is trying to use to say, do I believe this system is really ready to go or not? Because otherwise, they'd have to read through manuals that de-stack to the ceiling. So again, AI is being used in these kinds of situations as well. That's sort of conventional programming using AI to make it better. I want to spend a little bit of time talking about what's happening next. So in addition to making conventional programs better with AI, we should start thinking about how to make AI programs more resilient as well. It's a different kind of programming. Now, I'm going to repeat several things that you've heard many times before. Nothing changes. Everything that happened before will happen again. The usual tagline we say is that the Prince of Nigeria still needs your help. In this case, in AI systems like TensorFlow, very common one, we know, because we do these kinds of analysis, it has buffer overflows in it. We know it has null pointer problems in it. This is conventional kinds of stuff. None of that goes away when you have an AI system. You still need to implement the math correctly. But even when you implement the math correctly, there are problems that can result. So for example, as people early noticed, you can change individual pixels. And in fact, you can have some pretty dramatic kinds of changes. In this case, anyone wearing those specially generated glasses will be misidentified in a facial recognition system. And it's able to do that in an attack form because it turns out in most neural networks, you can extract enough of what the model looks like by pinging it enough times and getting the results back that you can start to then generate what a bad image would look like and how to fool the system. Similarly, if you look at different kinds of features that are in systems, you can start to say, not just at the pixel level, but at some of the, oops, oh my. Can I just say advanced? Will that work? Oh, thank you. You can identify intermediate places, and in this particular adversarial example, you could have this somewhat generated turtle toy look like a rifle. So what does this look like? How can you start to address this? And there's a whole set of things that are going on. So first, there's the idea of training the defenses so that they have a perimeter. That's sort of a layman way of saying that you do a delta epsilon of the actual pixel space. If you know that last part, that's fine. If not, what it means is that you start with what you think, what the system would normally classify something, that sort of arrow, that line that you saw previously. If you can start to draw little additional areas around what the answer should be, then as the adversary tries to move things, you'll still not misclassify it. Of course, you lose some precision that way, and it turns out that to do that is exceedingly expensive. That in the current technology, you can only apply these algorithms to handle like 300 by 300 pixel square kinds of things, whereas real images are typically much larger than that. Another one has to do with like that rifle example. You can actually start to feed it images where you say, well, you thought that you were being fooled, but I'm going to tell you that thing in the middle there, train it to say, that's still a turtle as well. Don't be fooled that it's a bird. You basically have to start feeding it the bad images as well. There's a bigger issue with all of these kinds of systems, and that is, and ultimately, this is math. And for deep neural networks, it's all based on statistics. So if looking around the room here, if I asked everybody to take out a penny and flip it, what do we have here? 6 times. It's almost certainly that one of you will wind up with 6 heads in a row, or 6 tails in a row. And you will be the lucky person who can publish a paper saying, you know, the mint doesn't generate fair coins because I flipped it 6 times in a row and it came up with 6 heads, and the odds of that happening p less than 0.05 or there, I found something magic. Well, with these kinds of AI systems, unlikely things can happen as well. All you can say is how likely is it that you found it versus how unlikely it was that it could be found, and how what your sensitivity is. This particular piece of research is giving some examples of that. What the current research is trying to do is make that quantifiable so that as you build your AI system, you can start to make precise and reasoned statements about how much risk are you willing to take of getting something wrong versus what's the impact of getting something wrong. The work in this area has been interesting, accelerating. Certainly, we're doing a lot of it. There is an unfortunate current technical circumstance. If you go to the academic conferences on this, you will find that people are publishing attacks and ways to get around those attacks. So far, to the best of my knowledge and to the best of the knowledge of my team who works on this, every single attack and defense against the attack has itself been defeated in less than 2 weeks in public forums. So people will publish a paper, and then within a week or two, someone will say, but here's how you get around that one. So there's a lot of work here still to be done. My point here is just to sensitize you that this is an area of work. And again, if you want to know more, there's plenty of references to learn about more. So what we focused on, that there is a need to build this software better, that just defending against after its attack is kind of too late and too expensive. You can look at the threat analysis, see what you're up against. You can actually work on building the software itself better. And we've got a whole new generation of things to worry about with AI systems. New kinds of attacks in addition to all the old kinds of attacks. Thank you again for coming, and happy to take any questions that I'm allowed to take. I say that because I see the timer is also running down.
We are running a little behind, so if you have any questions for Dr.